So what if your EV could charge in minutes, drive farther, and last for decades of use? Breakthrough battery tech is turning that dream into a reality. And some of the most exciting research is happening right here in Canada. In this episode, you'll hear about how and why service lifetimes of EV batteries have improved to the point where we expect battery packs to far outlast the vehicles they power. New cells made with single crystal electrodes show even more incredible durability, retaining nearly 80% of their original capacity after 20,000 charge and discharge cycles. That's equivalent to driving approximately 8 million kilometers or 5 million miles. These ultra durable batteries are out of the lab and they're now being produced at industrial scale. This talk will also cover how EV batteries degrade and how we can slow down that degradation, and why designing such long lifetime batteries is so important. Dr. Toby Bond is a senior scientist at Canadian Lightsource, Canada's national synchrotron facility. Toby completed his Master's of Science and his PhD in Dr. Jeff Dunn's lab at Dalhousie University, where he developed new tools to characterize and predict battery degradation. And in his current role, he works with battery manufacturers and automotive companies using advanced X-ray based tools to better understand how their batteries perform from the atomic level right up to the cell level. And on that note, Toby, a warm welcome to the panel and to the webinar.
Great. Thank you so much, Tim, for having me, and pleased to be here.
Oh, it's a great pleasure. It's great to have homegrown talent on the show. And we try and keep this webinar always with a little twist, some fashion Canadian twist or bent. And but you hit it right on the head here today. So we're really delighted to have you on and to hear about the work that you're doing.
Great. Looking forward to it.
All right. Well, listen, I'm going to get out of the way and turn the floor over to you, and you can have at it.
Well, thank you very much. Yeah, really pleased to be here. I've enjoyed quite a few of these webinars myself, so I'm in very good company. So before we get to talking about how EV batteries can outlast the cars, we're going to go kind of back to the beginning and talk about some of the basics, why EV service lifetime is so important. And I'll go into some detail about how lithium-ion batteries work, how they degrade, and then we can approach the question of how long they last. And there are different ways of approaching this using data from the field or data from the lab. But what I really want to get to is the work that we've done in the last few years, and this is a lot of work from my PhD thesis in Jeff Don's lab, using something called a synchrotron, and I'll explain what that is. To do X-ray imaging of batteries after long-term cycling. And this is data that is publicly available that we did academically, but in my kind of day job in the industry group at the Canadian Lightsource, I work with, as Tim mentioned, cell manufacturers and automotive companies to do this type of work to help their R&D efforts. So I do this all the time, but I can't usually talk about it. So it's really nice to have some data that I can share. We'll first talk about kind of conventional batteries and show how they work after long-term cycling, and then we'll talk about kind of the headline, which are these single crystal electrodes, and answer the question: can they really withstand 20,000 cycles and the equivalent of driving 8 million kilometers? And so we'll not only show that they can, but we'll go under the hood using this X-ray imaging and explain how that's how they look after that much cycling. So to give you some context, obviously we want batteries to last as long as possible, just for the sake of economics. We want the life cycle cost to be low. We want the life cycle carbon footprint to be low. So we want them to be economically and environmentally sustainable. But when we're talking about these batteries that are going to last, decades, tens of thousands of cycles, you start to wonder, okay, is this overkill? Why are we designing batteries that last so long? And one of the important reasons for this are, new technologies like vehicle-to-grid storage, where we can use electric vehicles as a distributed energy storage resource by charging them from the grid, but also discharging them back into the grid so that the grid can use them as power, as energy storage for intermittent renewables. The downside to doing this potentially is that you have to put the EV battery through much larger number of cycles. And so we want to make sure that EV batteries can withstand a really large number of cycles, that's much higher than you might use it just for actually driving. Another important and kind of emerging area is something called second life storage, where at some point, as the capacity kind of fades over time from its original value, the ability to store charge of the battery fades over time. We want to use, we get to the point where it might not work for EVs anymore, but then we could use them for some other application where the energy density isn't so important. So a good example of that would be grid energy storage, where you could take a bunch of used EV batteries, put them in a field somewhere next to a solar power plant, and just have them sitting in a bunch of sea cans. And if you need more energy, you just add more sea cans. You don't necessarily need them to be very dense anymore. And so eventually we need to recycle them, but recycling is an energy intensive process. So we want to really extend the battery lifetime as long as we can. And for grid storage applications, we really should be talking about batteries that can last for decades and thousands or tens of thousands of cycles. And moreover, we need to understand how these batteries behave after the kind of first life is over. We want to make sure that they degrade in a very predictable way, so that we can kind of model them and finance them in a way that's sustainable. And I should mention too that there's a Canadian company doing this type of second life storage called Moment Energy out of BC. This is kind of taken off, I'd say, more in Europe right now, but in North America, it is starting to grab hold, and there's a major Canadian player that's doing work in this space. So it's very exciting to see. Okay, so let's start at the beginning. Before we get to the cool science, I think it's worth going through some of the basics. So this is how a lithium-ion battery works. If you go down to the atomic level, when you charge a battery, lithium ions move back and forth between two electrode materials. One of them is called the negative electrode, which is almost always graphite. And at the atomic level, this is what graphite looks like. You have these layers of carbon atoms that are all linked together in these sheets. And in between these sheets, there are spaces for lithium ions to move into. On the other electrode, which we call the positive electrode, it's typically a transition metal oxide. And the two most common electrodes that are used in North America and Europe are one's called NMC, which stands for nickel manganese cobalt oxide. The other one is called NCA, which stands for nickel manganese aluminum oxide. And they're very similar materials. They have the same kind of basic structure and a lot of the same behaviors. So I'm going to kind of lump them together today. The data I'll show you is for NMC, but a lot of it really extends to NCA. So I'll also mention briefly lithium iron phosphate. It's not going to be the focus of the talk today, but it is an emerging EV material, and it's the dominant material in China. But I wanted to keep this relevant to Canada, so we'll mostly be talking about the other two. But I will have one slide on it kind of at the end. And then aside from the electrode materials, we have this electrolyte solution, which is a liquid that has dissolved lithium salt. So that's where the lithium ions actually come from. So in blue here, that's just a fluid that lithium ions can move through to get from one electrode to the other. Then we also have this separator, which is just a porous polymer membrane that allows lithium to go through, but doesn't allow, pardon me, doesn't allow the electrodes to come into contact with each other, which would cause a short. So to give you a sense of what the EV battery looks like, if you start tearing it apart, you'll see it's made up of a whole bunch of modules, and inside those modules are a bunch of cells. Those cells can have different form factors. So they might be cylindrical cells, which is commonly used in a lot of Tesla and BMW EV battery packs. And then in other battery packs, you might see these rectangular cells. Either a pouch cell, which is kind of in a vacuum sealed aluminum bag, or a prismatic cell, which is in a rigid steel container. And inside of those cells, these layers of electrode material are kind of either stacked or wound around each other. And so, you have in this kind of golden tan, that would be the graphite, the negative electron. And then in black, you have the positive electrode, the NMC or NCA. And in this case, we're going to talk mostly about pouch cells with prismatic windings, but just to give you an idea, they can have lots of different structures. So if we zoom in on one of these layers, this is what the kind of the microstructure, the microscopic structure of a graphite negative electrode looks like. It's kind of these flake-like particles, and they're pressed into a thin layer on a copper foil. And if you look at the positive electrode, NMC and NCA, look something like this. And so there's these little balls that we call secondary particles. And if you zoom in on those, oh, before that, these balls are kind of held together with a polymer binder that has a conductive additive so that you can conduct electricity between the balls and out to the terminal. If you zoom in on the secondary particles, they look something like this. And you'll notice there are these little grains, these kind of subparticles, which we call a crystallite, or you can also call it a primary particle. And you can think about this like a snowball. A snowball is just a bunch of snowflakes packed into a ball. And so you could think of these crystallites as being snowflakes, individual crystals of electrode material that are packed into these kind of micro snowballs, if you will. So that's the kind of the basic structure all the way from the electrode, the particle level up to the pack level. So why do batteries degrade? Well, there are a lot of different ways they can degrade. And if you're a battery manufacturer, you have to know what all of them are and how they interact with each other. But I can give you kind of the short answer. It's that electrode materials react with the electrolyte. That's the most important general kind of process that's going on in a lithium-ion battery that causes degradation. And so if you zoom in at the negative electrode, so these are particles of graphite over here, and we look at this surface, once that surface comes into contact with electrolyte, it forms this surface film. In technical jargon, we call it solid electrolyte interphase, or SEI, but I'll just call it surface film because that's easier to remember. And initially, you form this kind of thick surface film, and over time, it'll keep growing a little thicker and thicker. But as time passes, the subsequent layers get thinner and thinner, and that's because this layer actually protects the graphite from this further reaction. So it's very reactive initially, but if it forms a nice stable film, then that'll prevent it from reacting quickly, and so it'll actually slow down the rate of reaction over time. The reason this causes degradation is because lithium ions actually get trapped. They get incorporated into this film, and so then you can't use them to charge and discharge the battery anymore. And each of these lithium ions that you lose means that you lose one electron that can't go to power your car anymore. On the positive electrode side, you also have reactions at the surface, but they tend to be a bit different. One of them is something we call electrolyte oxidation. This tends to happen at higher voltages, so higher states of charge. You can also, in some cases, have gas formation, so you can have oxygen or other gases be evolved at the surface. And the third reaction that's concerning is what we call restructuring or rearrangement of the cathode of the NMC. And so this happens at the atomic layer, and the problem with this layer is it hinders lithium ions from actually getting across into the electrode, into those spaces where it's stored. And so this slows down, makes charging slower. It means that you don't get as much capacity that's accessible to the battery. And so these are all surface reactions. So, generally we want to reduce the surface area, and we can slow down these reactions by limiting the exposure to high temperature. So higher temperatures cause faster reactions. So we do this by cooling the pack, ideally with liquid cooling. We want to limit the voltage. So if your battery doesn't always need to be at 100%, better to leave it at a lower state of charge, generally speaking. That'll slow the reactions down. On the manufacturer side, they'll always be on the lookout for really good electrolytes and additives that they can add to make stable surface films and slow down these reactions. And then they can also try and use electrode materials that are more stable, that have coatings, or that are just high quality materials and don't react as quickly. So aside from these internal reactions, there's another problem that kind of plagues these NMC, NCA materials, and that's something called electrode microcracking. So if we go back to the atomic level, this is what the positive electrode looks like when it's full of lithium ions, which I've labeled here in green. And when you remove those lithium ions, the material actually shrinks. And so this happens at the atomic level. And the problem with NMC and NCA is that this shrinking doesn't happen the same in all directions. And in fact, in some materials, it can actually expand in one direction while it shrinks in another direction. And so this non-uniform shrinking can cause all sorts of problems. If you have one of these secondary particles, one of these snowballs, at different orientations, then you'll get a really complex kind of distribution of stress and strain within the particles. And that eventually, after repeated expansion and contraction, that'll lead to a lot of fatigue and eventually what we call microcracks. And if that microcracking gets severe enough, it'll actually break open the particle and electrolyte will be able to go inside of it. And so if you think about all of these reactions I was just talking about, initially, this red area out here on the boundary of the particle, that's the electrode surface area that's exposed to the electrolyte. But if the electrolyte is allowed to get inside, then you have all this extra surface area that is now exposed. And so this increases the rate of those what we call parasitic reactions that we don't want, that remove capacity from the battery. And so this is what microcracking looks like in an electron microscope image. So I'm not just making this up with diagrams, it's very much real. And so you can see these little crystal grains, these crystallites, they're a little bit faint, but it's a lot easier to see these cracks that form along the boundaries between them. So in general, I would recommend that everyone check out, if you haven't already, Jeff Dawn's webinar from this series on maximizing your EV battery life, because he will touch on in much greater detail how to operate your battery in a way that kind of prevents microcracking and these parasitic reactions as much as possible. But I'll just quickly summarize, because I'm sure people are curious to know if they haven't seen it, some of the major tips and take homes from that. It's best to keep your battery below 75% if you have an NMC or NCA battery pack, which is most battery packs in North America. Just because it limits that voltage, keeps it lower, and then it also means you don't expand and contract the electrode as much. On the same note, if you can do more frequent charging and discharging rather than infrequent but deep charging and discharging, that's better. Again, because it just limits the amount of that volume change and it limits that fatigue. So something like between 45% and 70% state of charge is kind of ideal. And if you're leaving your EV for a while, like for weeks or months, best to leave it at a lower state of charge to keep that voltage down. So say something like 30%. But if you need to charge it up to 100% for long trips, by all means do it. But if you want to kind of get that extra service lifetime out of your battery, these are the main ways to do it. But I'd suggest you check out Jeff's webinar, because he'll explain the reasons behind all of this in exquisite detail, and I won't cover all of it today. Okay, so now we can get to the question of how long do EV batteries last? And I'll give you the unsatisfying answer first, that it depends. It depends on a number of things. It depends how we define the end of life. And we will often use some kind of arbitrary number like 70% or 80%. And I'm going to use 70% just because that's typically where most warranties are voided. And so when you have this degradation of capacity, so the amount of charge that the battery can store over time, we call this capacity fade. It typically has this kind of shape to it, where you have this kind of initial a steeper loss of capacity, and then it kind of plateaus out and it's slower. And this comes from that effect I was talking about before, where you have that initial fast reaction of that surface film, and then that surface film makes the further reactions slower and slower. So after that point, it might keep going very linearly, very regularly. Or if something is wrong with the battery, you might have what's called rollover failure. And so you could have this kind of accelerated loss of capacity. And microcracking is one way that this can happen. If you have really extensive microcracking, you have all that extra exposed surface area, and it kind of accelerates the rates of those reactions. There are many different ways that can happen, but this is an example. This doesn't happen magically at 70%. It could happen anytime. It might happen later. It may not happen at all if the battery is very stable, but it's something that can happen. So it's just something to be kind of aware of. And preventing this rollover failure is really important so that we can use these for, as I mentioned before, second life applications. I should mention that when we talk about battery lifetime, we're usually talking about two different things. One of them is what we call calendar life, which is the lifetime over time. So if your battery is just sitting there, those parasitic reactions are slowly, very slowly occurring, no matter how much you drive it to some extent. So you will still lose some capacity over the calendar life of the battery. But in terms of mileage, we're talking about something called cycle life, which is more things like microcracking that depend on how many times you've charged and discharged or cycled the battery. But the two can be related, right? If you cycle it, you can cause faster calendar aging and so on. So now we can actually start to assign some numbers to this. I'll give you at least the floor for how long a battery will last. It's got to be a minimum of 8 years by US federal law, which pretty much extends to us in Canada, or 160,000 kilometers. If it goes below 70%, or whatever the indicated percentage is, by the manufacturer over that time or that mileage, then the manufacturer has to replace the battery. But I want to mention, I want to stress that this choice of 70% is totally arbitrary. If your use case allows for it, you could let it go down to 50% or 30%. If you're only commuting, maybe that's all you need. And essentially your range just goes down over time. So it's very much use case dependent as to where that cutoff actually happens. Okay, so now let's look at some real data. There are kind of two ways to approach this idea of battery lifetime. One is to look at historical data from the field, and another is to do kind of predictive experiments in the lab. So if we look at some recent field data, this is a study from P3 and Avalue. Avalue is a battery diagnostics company. This is data from about 7,000 EVs. I think they're fleet EVs that came off lease. So each one of these blue dots is a capacity measurement at a specific mileage. So it goes up to 300,000 kilometers. On the right here, and you can see this average line here for all that data does pretty much what I was showing you before. There's an initial faster kind of decay, but then it pretty much levels out. And at the end of that, the average is just under 90%, so doing very, very well. And you can see, though, that these dots can vary quite a lot depending on the usage conditions, the model, the chemistry being used. There are a few, outliers here that'll drop below, and most of these will get caught by the warranty, but it's always a risk. But the average is very much clear. You're still doing really well for cars that were, I think this was from 2019 to 2024. There's another study that Geotab, another fleet management telemetrics company, involving 10,000 electric vehicles that came off lease. And they did the same kind of thing. They measured their capacity. They did this study back in 2019, so that covered the years from 2014 to 2019. And at that point, the average capacity fade was 2.8% per year over the first 5 years. So that includes that initial kind of drop. And when they did that again in 2024, that was 1.8% per year. And so that's getting really good, and it's improving substantially. And so they estimate we're getting at least, should be more than 20 years of lifetime out of that. And they mentioned in their report that this should be more than enough to outlast the lifetime of a typical EV. So what I'd like to stress right off the hop is that we're pretty much already there in terms of the historical data. But the drawback of doing it this way is that we can only look at historical data, and we can't predict where current battery chemistries and developing battery chemistries are going to take us. So to do that, we need to do experiments in the lab, and we need to do experiments that are going to take, less than 10 years. We don't have the luxury of time to just cycle them for as long as we'd like and then see how long they last. We need to do some kind of accelerated controlled testing. So we have these temperature control chambers, and each of these is hooked up to a channel that very carefully charges and discharges the battery, takes very high precision measurements, high precision current and voltage. The temperature is very carefully controlled, and we do regular predictable cycles. And we know everything about the battery. We know each cell, we know its chemistry, and then we can systematically vary it to do this kind of accelerated testing. So we'll often do deep cycling. We'll often store them at higher voltage. We'll store them at high temperature. We'll do things to kind of accelerate the aging process so that we can measure this capacity fade for a bunch of very similar cells, and then kind of predict from these initial measurements which ones are going to be better. So the ones at the top here, like in red and black, those would be the better performing cells compared to these green ones, which are aging faster. And I'm just going to mention very quickly that there's a lot more to it than what I've described here. There's a lot of complicated electrochemical measurements that we can take that I'm just not going to go into detail about today. But there's a lot of characterization and a lot of information you can get from doing this type of testing. But at a certain point, you want to actually look inside the battery and see what's happening, see what's happening in the chemistry kind of under the hood. So this is one of these pouch cells, and I'll talk about this a bit more in a bit, that we use for testing in Jeff Don's lab at Halifax. And if we disassemble it, we can access the electrode material inside it, and we can either do lab tests, chemical testing, or we can put it in an electron microscope and look at it. This is the best way to get the most information, but it involves sacrificing the cell. And sometimes if we're cycling these batteries for years, they're really valuable, and we want to use non-destructive testing to look at them without having to take the cell apart. So this could be things like ultrasound or X-ray, and I'm just going to talk about X-ray today. So if you've ever had an X-ray, which most of us have, it's a pretty straightforward procedure where you have an X-ray source, it shines an X-ray beam through an object, and then you have an X-ray sensitive camera or detector behind it, and you basically take a picture of the shadow that that object casts onto the detector. And if we want to extend this into 3 dimensions, we can take what's called a CT scan or computed tomography scan. And if you've ever had one of these scans done in a hospital or a clinic, it's essentially the same thing as an X-ray, but they take X-ray images from a bunch of different angles. So you go into one of these tubes, and then they rotate an X-ray camera and source around you and take a bunch of images at different angles. Then they can reconstruct those into a 3D model that has all the internal structure of your organs and bones and whatnot. And we can do the same thing with a battery, and we can see the internal structure of the electrodes and all the kind of structural changes that are happening inside the battery. But if we want to get really advanced with this, then we need to kind of kick it up a notch and use a more powerful X-ray source than kind of an X-ray light bulb that you would see in a hospital CT scanner. So we can use what's called a synchrotron, which is, I like to call it the X-ray on steroids. So what's a synchrotron? It is a X-ray source that uses a particle accelerator to produce what I call laser-like high intensity X-ray beams. And so these are very kind of parallel focused beams that are very, very bright. It's kind of, X-rays are really just a different form of light that you can't see. They have very high energy that can penetrate through objects. And synchrotrons are capable of generating very bright X-ray light, if you think about it that way. And so an X-ray, the particle accelerator involves accelerating electrons in our case to very close to the speed of light. And when you do this in a ring like this, it gives off these X-ray beams. We have about 20, I think 22 of them at our facility. And each one of those beams we can use to do different kinds of experiments. And there's lots of things we can use X-rays for in science. I'll only talk about imaging today, but we can do studies at the atomic level. We can look at chemistry, all sorts of different things. So each one of these structures, which is called a beamline, can be used for a different purpose. This is what our facility looks like. This is the Canadian Light Source where I work in Saskatoon, Saskatchewan. This was commissioned about 20 years ago, and it's been operating since then, and it's Canada's only national synchrotron facility. This is a nice aerial view of Saskatoon skyline, and that's our facility right there on the University of Saskatchewan. Okay, so if you do a synchrotron CT scan, it's essentially the same basic idea. You just swap out an X-ray light bulb for one of these synchrotrons, and then you shine the beam through it, and you take a picture with an X-ray sensitive camera, rotate the sample, and you get your scan. And so this is what it looks like when we do these scans at our facility using one of these batteries. And so this is the size of battery that we use. These are kind of smaller scale prototyping batteries, but they're still machine made. They're still commercially manufactured and very representative of what you'd have in an EV battery. So the light shines through this, and then we have the detector back here that captures the images, which can go down even to the microscopic level. So the reason we'd go to all this trouble and use a synchrotron instead of a regular kind of hospital CT scanner, they're very, very fast because you have a very bright X-ray beam. It's like taking a picture with a flash compared to taking a picture in a dark room. You can collect your data much, much faster. You get your picture much, much sooner with a much shorter exposure time. So we can do really cool experiments, and I'll show you a couple examples in a minute. You also get really good contrast, so you get really good quality images. And importantly for us, you can see really, really small features, like microscopic features inside large objects. And it turns out that's really difficult to do with a conventional CT scanner. So this allows us to see microscopic levels of detail inside of a battery, in a commercial battery, that without having to disassemble the cell. And even though I'm showing you data from these smaller cells here, we've actually done this for clients, for example, with real EV cells that come from an EV battery pack. So we can do this with much larger batteries as well. Okay, so this is what one of these CT scans looks like of one of these pouch cells. And you can see this wound jelly roll structure I was talking about before. And if we go inside of it, you can actually see these kind of internal details, like there's a little bit of a damaged region here for this cell, for example. And although we have these 3D renderings, I'm mostly going to show you these kind of 2D slices. They're like a little 2D plane or thin section that we pull out from this data. And it's just because you can see more detail. But keep in mind that everything I'm showing you is actually coming from one of these 3D data sets, and you can move through it and look at any part of the cell that you want. So we can do these at the full cell level, capture the entire cell all at once, and we can zoom in using a synchrotron and go to really, really high detail. So we can actually see these layers of electrode material I was talking about. There's the copper foil and some graphite, and then here's some positive electrode material on some aluminum foil. And we can go right down to the particle level. And just for scale, one of these layers is about the width of a human hair. And so without taking the cell apart, we can actually see these minute little details like microcracks without even having to disassemble the battery, which is pretty amazing. And since we don't have to disassemble the battery, you can actually see the battery operating in real time. And so this is an example of what we call breathing, the expansion and contraction of the electrode. So before, when I talked about this, lithium ions going in and out of the material, you can actually see this on the microscopic level. You can see that this is the graphite in this case expanding and contracting as you charge and discharge the battery. I'm not making it up. The material really does expand and contract, and this is what causes that fatigue that I was talking about before. Okay, so we want to look at these long-term cycled cells, and I'm going to use 3 of them as an example. And pretty much everything I'll show you will involve these 3 cells. So there's a fresh cell that has not been cycled at all, so it's like fresh off the production line. There is a lightly cycled cell, which we cycled using shallow cycling. So we cycled it between 75% and 100% depth of what we call depth of discharge. So 75% to 100% state of charge. And this would be the equivalent to driving just under 400,000 kilometers. So it's pretty good. And you can see this initial dip in capacity that we often see because of that surface film that forms. But then it really flattens out. In fact, it looks almost totally flat here. And you can see what a difference this makes compared to this other cell in red, which I'm going to call the heavily cycled cell. This cell we cycled, first of all, we cycled for longer. So it was 2.5 years compared to more like 1.5 for this guy. And we cycled it for 2,400 cycles, which is the equivalent, if you have a 400 kilometer range EV, that's the equivalent of driving just under 1 million kilometers. And we cycled it from 0 to 100%. So this is very abusive conditions. You would never cycle all the way down to 0, charge all the way back to 100. But if you did, this is the kind of difference in capacity fade that you would get. So it makes a big difference off the top. We don't need a fancy synchrotron to see any of this. You can tell it just from this data. And so these are cells that have kind of moderate energy density. It's about 60% nickel. So the more nickel you add, the more lithium you can store, and the more energy the battery can store. So if you have more nickel, you essentially have more of this volume expansion and contraction. And we cycled these cells at 40 degrees Celsius. So probably a little bit warmer than you would have at the operating temperature, but not that much warmer. It's kind of a typical value. But these 3 cells are going to be kind of a useful. They cover the range of use cases from not cycled at all to lightly used to kind of abused. So if we look at the fresh cell and go straight down to this particle level CT scan, you can see that the particles look very healthy. They're nice and dense. There are some little cracks here where these blue arrows are pointing, and that's probably from the manufacturing process where they get kind of a lot of pressure is applied to them during the kind of coating process. So you get some cracks initially, even in a fresh cell. If you compare that to the lightly cycled cell, you'll start to see some little cracks prop up here and there. I'd say there's more cracking going on here than in the fresh cell. But if you look at the heavily cycled cell, then it's a very different story indeed. The material is almost completely disintegrated, and there's so many cracks. You can tell that there's probably electrolyte filling all of these cracks and infiltrating the snowballs, the secondary particles I was talking about before. And when these cracks appear, when it's so extensively cracked like this, the layer swells up. So this layer is a lot thicker than these other layers because there's a lot of extra empty space in here. And so there's much more exposed surface area. The battery is kind of swollen, and that can lead to another effect, which we see if we look at the cell level CT scans, where if we start with a bunch of extra liquid electrolyte, which is this kind of light gray here, this dark gray is just pockets of gas. Even in the lightly cycled cell, most of that electrolyte that extra electrolyte is gone after a year and a half of cycling, of light cycling. And for the heavily cycled cell, it's completely gone. There's nothing left. And the reason for that is because we have all that extra space, all of that swelling, and all of that what we call pore space up in the electrode. At a certain point, the electrolyte gets sucked up into it. And if there's not enough electrolyte to go around, then you start to have certain regions that are going to actually be dried out. And this is another thing that could cause rollover failure, because you have this kind of critical point where you start to run out of electrolyte, and then the lithium ions can't move through it as easily anymore. So these things are all linked together, and they're all a result of microcracking. I should mention, though, that even after all that abuse, this is still in warranty in terms, it's still above that 70% threshold. So this is for a conventional material, just under 1 million kilometers under these abusive conditions, for a 60% nickel material, is still doing really, really well, and still, should easily outlast the vehicle itself. But we'll show you how we can do even better than that in a moment. So another nice thing that we can do is we can actually show, because we don't have to take the battery apart, we can actually track this microcracking as it happens over the lifetime of the battery. So this is a time lapse where we took a CT scan every 200 cycles, and each frame, basically there's 7 frames, and they cover 1,200 cycles of charging and discharging. So you can see this expansion, the swelling that I was talking about, and you can see the centers start to get dark and kind of hollow out, and these cracks start to kind of form. So you can actually look at the onset of this process as the battery ages. And then you get some interesting information about how the material deforms, how the structure of the particles and the pore space changes over time. Okay, so that's all great. How do we stop it from happening? There are a number of different ways that have been tried over the years, because this is a very well-known problem. Usually in the past, this has involved some kind of doping, adding something to the material to help stabilize its crystal structure, or applying some kind of coating that kind of keeps it from expanding and contracting too much, or modifying the structure somehow. But I'm going to focus on this one particular type of material called a single crystal positive electrode. So what this is these snowballs I was talking about before. In our technical jargon, we call this a polycrystalline material. And that's because there are many crystallites inside each particle. But a single crystal electrode has just one crystal, one big crystal in a particle. So since we have this cracking happening along these boundaries, one way to get rid of that is to just not have the boundaries anymore. And it sounds pretty straightforward, and it turns out it's very, very effective. So if you think about these polycrystalline particles as being a snowball, a single crystal particle is more like an ice cube. It's just one big solid crystal, and it's much more durable. If you squeeze a snowball with your hand compared to squeezing an ice cube, it's a lot easier to crush the snowball than it is to crush the ice cube. So that's kind of a good analogy for how these materials behave. So we compared a single crystal cell that's been cycling over in the lab in Halifax for over 6 years now. This cell already got pretty famous when it hit the 1 million mile mark, so about 1.6 million kilometers, but now it's up to about 5 million miles, or 8 million kilometers, which is, roughly 20,000 cycles. So you can see the capacity fade here. Again, still, just a bit past 80% and not even at 70% after 6 years of cycling, 1 hour charge, 1 hour discharge constantly day and night, which is pretty incredible. And this is deep cycled. Both of these batteries were deep cycled. So this is the heavily cycled material, the heavily cycled cell I was just showing you in blue. And that's how fast it degrades, which again, isn't fast. It still lasted a good while and it was abusively cycled, but the single crystal material just does so much better. So even it has 10 times the number of cycles roughly, and it reached the same amount of capacity fade, and probably still has a lot left to go. It's still cycling in the lab as we speak. So yeah, it's just amazing that how good that capacity is after so much time. But we really want to look under the hood and see, how does the cell look? Did it also get pulverized? Is it, at 80%, but could fail any minute? Well, if we compare this to the data we just looked at, where you have this extensive swelling from the fresh cell to the cycled cell, in the single crystal material, there's no change. We actually don't see any swelling, any growth of the thickness at all. We don't see any evidence of microcracking. And if we look at the electrolyte before and after cycling, this was for the polycrystalline material I mentioned before, you see some loss of this electrolyte, but there's plenty of it left. And again, after 6 years, that's pretty incredible. So if I was going to look at these cells and evaluate them for use in a grid energy storage as a second life application, I would, even though these cells have about the same level of capacity loss, I would much rather be using the single crystal cell because it's much healthier. There's lots of electrolyte left. There's no evidence of this microcracking. It should continue to degrade in a very predictable way. So that's why it's really important to have techniques like this where we can actually look under the hood and see what's going on inside the structure of the battery, because otherwise we wouldn't know. We would just say, okay, the state of health is 75% for both these batteries. But if you go in and you actually look at what's happening inside the battery, you can tell just how much healthier in kind of a holistic sense the single crystal cell is. Okay, so I get a lot of questions about these electrodes, and probably some of them will come up in the chat, but I'll maybe preempt a few of them here. Are there any drawbacks? It's important to always look at this. There's a lot of hype in batteries, and I want to always be honest about the drawbacks. So historically, they've been trickier to make. The synthesis, the manufacturing of these materials has been more finicky. You have to kind of carefully control the temperature. And there are kind of different methods to get the same type of crystal growth. But now there are lots of methods out there. There are many companies who all have different patents. They all have their own secret sauce for making these single crystal materials. And it's much more known quantity than it used to be. Historically, they were also more expensive because they were more difficult to make. But that premium is pretty much gone now. It's last time I checked, I think it was maybe something like 5%. So maybe a little bit more expensive, but considering the life cycle cost, it's kind of a no-brainer, I think, for most applications. One other drawback is that because you have these larger particles, the lithium movement is a bit slower. So it moves more slowly through the bulk particle than it does through those grain boundaries. So we have to use smaller particles, and you might have noticed that here, right? These were big particles here, and we use small ones here. So we have to start with more exposed surface area. That's how we can keep the particles from the lithium movement through the particles kind of fast. But it's a bit of a drawback. We have to kind of engineer the particles for that. And so if you're not doing that, then you'd have a less rate capable material. It wouldn't charge and discharge as slowly. Really big question: are they used in electric vehicles yet? I can tell you that cells are being mass produced by major manufacturers, and they are probably being deployed in EVs, but I can't point to any specific models. I don't know of any publicly available information that has identified a specific model as using these in production yet. So it's tough to confirm which models may or may not be using them. But large companies that have publicly disclosed this include CATL and S-Volt, so two really major Chinese companies that are making it in very large quantities. And there's also a Korean company called LG Chem, which is making them in really large quantities, and they've publicized a supply agreement with General Motors. So, essentially they're being made in cells at commercial scale. I wouldn't be surprised if they are being used in EVs, but I can't tell you which models, unfortunately, yet, as of the airing of this webinar, which is May of 2025. But hopefully we'll know in the not too distant future. I should mention too that there are a couple of Canadian companies who have patents in this space, one called Nano One out in BC and another one called Novonix, which was actually a spin-off out of Jeff Dunn's lab in Dartmouth, Nova Scotia. So there are a lot of different companies in the space, and it's certainly being produced at scale, and it's kind of a swappable replacement. I know that a lot of automotive companies are at least validating and evaluating their use. I just don't know which ones have actually put them into production yet. Okay, and then one last slide, because I mentioned I would come back to lithium iron phosphate. Is microcracking a problem in LFP? Not as much is kind of the short answer. So this is because that volume expansion I mentioned, it still happens, but it's not as uniform. And the particles in LFP are tiny. So this is some research by a lab mate of mine, Eric Logan, who looked at microcracking in LFP. And this is a typical material over on the right here in a fresh cell on the top and then an aged cycled cell on the bottom. And these particles are very, very small. They're, tens, hundreds of nanometers in size. So the microcracking isn't as big of a problem when you have really tiny particles. But if you have large particles, then you actually do see this microcracking. So it can be an issue, but it's just not as big of a problem compared to NMC and NCA. The reason you can have these tiny particles is that LFP batteries are much more chemically stable. They operate at lower voltage, and so they don't react as much with the electrolyte. And so you can actually have these tiny particles to start with and have all this extra exposed surface area, and it's not as big of a deal. And so LFP, I should mention, because of this, it's got really, really good lifetime as well. It's just not, it doesn't have as good energy density. So it's not as popular in North America, but it's the dominant battery chemistry now in China. And I should mention, the best battery warranty I've ever heard of is from a CATL LFP battery, which is one of their, the Tianqing bus battery, which is warranted for 15 years and 1.5 million kilometers. So again, it should last well beyond that. That's what they're willing to warranty, which certainly says something. But yeah, like I mentioned, LFP has some drawbacks, which is why it's not as widely used in North America. It's got lower energy density, so you have less range. So you can't accommodate as much capacity fade, but it is a very good long lifetime material. Okay, so to summarize, EV batteries can already outlast the cars they power. So if you were really drawn to this talk by the title, I can already tell you that based on the historical data, we're basically there already. But newer chemistries are going to last even longer. And in particular, single crystal materials are really, really promising, especially for these kind of vehicle to grid second life applications when we're talking about tens of thousands of cycles and decades of calendar life. So if we use these materials, you don't have to worry about cycle count, and the battery is in much better shape after extensive cycling, which makes it, lends itself to these applications. And synchrotrons are really useful, for understanding what's going on under the hood. If we want to actually look inside these batteries and see how healthy they are, it's really useful to have facilities like this in Canada to be able to do this kind of work. And I should mention, just put in a quick plug for the group that I work at with the CLS. We do this type of work all the time for private sector clients who want to do this as part of their R&D. It's completely proprietary and confidential. You just have to hire someone like me to do the experiment for you, essentially. So if you're interested in that, you can go to our website, lightsource.ca, or email me directly. And with that, I'll leave it there and just want to thank Jeff Don, my PhD supervisor, and Sergey Gaslov, Graham King, our scientists at the CLS who helped me with a lot of this work, and all the other students in the Jeff Don lab at Dalhousie who contributed to it.
All right. Thanks. Thanks very much, Toby. I have a bunch of questions, but I'm going to table them because we don't have a lot of time. And I know that Jason, I think you have some questions. I see them queuing up. And if you would you jump in and fire them at Toby?
No problem. And I'll start with an easy one. Leo asks, is it possible to get a tour of your facility?
Absolutely. Yeah, we run public tours, I think 3 times a week. So drop by anytime. It's totally free. If you know me, you can shoot me an email. And if I'm around, I'd be happy to show you around. It's worth seeing. It's quite a sight. It's a massive accelerator. And if you're at all a nerd about this kind of stuff, then it's absolutely a must-see attraction if you're in Saskatoon.
I asked the same question, so I'm going to hold you to it.
Yes, everyone is welcome. The more the merrier.
Okay, Tim provides an example of Ford Canada suggesting charging to 90% for daily use, whereas you said below 75%. He wonders why the manufacturers and the scientists don't get together and give the same advice.
Yeah, so part of that is because it depends on what specific chemistry you're talking about. And 75% is an important number, specifically if you have kind of a really high energy density material that has more than 70% of nickel. So if you have a long range EV, you probably have one of these high nickel, what we call nickel rich materials. And those materials have kind of a specific inflection point at about 80, just above 75%, where that volume expansion increases significantly. So that's why we put the number there, so that it's kind of a catch-all and it's a safe number. So a lot of manufacturers, if you look at your manual, might say something different, and that's totally fine. That means you probably have like a lower nickel material. It's tough to come up with guidance for every kind of battery chemistry. They'd be different for LFP, for example, too. So we tried to come up based on, we tried to come up with kind of the broadest rules that we could. But if you follow your manufacturer recommendations, those will be fine too. And again, it's not a matter of like, if you go above 75%, you're going to trash your battery. You can deep cycle it like I showed you, and you'll still get really good performance and really good lifetime. And I think it's really important. I want to stress that point because it's easy to get neurotic about this stuff if you think about it too carefully. But really, these materials are all meant to be durable. They're all meant to be long lasting. You can use it as much as you want without thinking too hard about it. But if you have the option, if you have access to charging at home, it's better if you leave it at a lower state of charge. If you're just using it for commuting, you're just going back and forth, you're better off charging it every night if you can, than letting it go all the way to 0 and then charging it all the way back up, or keeping it at 100% all the time. These are just things that if you have the option, it's better to do, and you'll get extra lifetime, well past the manufacturer's warranty. So excellent question. And I'd encourage you to watch Jeff's webinar because he'll go into more detail about where those numbers come from and why we use those numbers. Yeah.
For good reason. That particular episode that Jeff did is the most viewed one that we've ever done in 4.5 years of doing this. And I will put a link to that in the comments or in the notes section below this recording of this video so people can find it quickly.
Okay, on a different note then, are sodium batteries close to being installed in EVs?
Yeah, so excellent question. Sodium batteries are very exciting. They've come a long way, and they certainly are being produced at commercial scale. Back in 2022, when lithium prices were through the roof, they were very attractive in terms of cost. But now they've hit a bit of a plateau, and this might be temporary because they are, even though sodium is a lot cheaper than lithium, lithium iron phosphate has become so cheap that that actually makes up the difference. Sodium ion batteries are much less energy dense than certainly than NMC and NCA, and also and even less energy dense than LFP, and they're really competing with LFP. And right now they're not competing in terms of cost, but that could change easily if lithium prices change. It's kind of a fluid situation, and they have a lot of capacity to manufacture them. I would say the major barrier to them being adopted in EVs is still their energy density. They're still a bit below lithium iron phosphate, and so you'd only really see them for short range EVs, maybe something like less than 300 kilometers, if I was going to pull out a number. And so in North America, that's a tough sell, especially in Canada, since we don't have that great of a charger network. Eventually, when we do have a charger network, I really hope that these shorter range EVs will see more widespread adoption. I think in China, you'll start to see sodium ion batteries be adopted in the not too distant future, or you'll see hybrid packs. There's one made by CATL that has some sodium ion modules and some lithium ion modules. And so there are ways that it'll be integrated, but I don't think they're going to be replacing lithium ion batteries wholesale anytime soon. And you probably won't see them in North American EVs for some time.
Okay. One comment from Lawrence saying that I've seen a number of studies that indicate EVs used for V2G experience less battery degradation than EVs charged casually for transportation. Do you have any comments on that?
It's interesting. It's tough to know from when you get data from the field exactly what happened. If I had to guess, you might see something like that if they're being used in V2G applications and they're being kind of charged and discharged around a lower state of charge, so the average voltage was lower, compared to maybe somebody who was using it for transportation and charging it to 100% all the time. Maybe you could come up with a difference that way, but you'd have to have some difference in the use case. It's not obvious to me why that would be, and I'd want to, it's tough to say without knowing what the actual specific charging conditions are in that case. And from field data, that can be tough to tell.
I think, Jason, we could probably squeeze in one more if it's not a long one.
And you're going to groan when I ask you this one, because this definitely could probably be a webinar by itself. What's the difference between single crystal and solid state?
Good. Actually, I can give you a pretty quick answer to that. Single crystal positive electrodes can be used in solid state batteries, and actually likely will be. So solid state batteries refer to having a solid electrolyte. Instead of a liquid, you have the negative electrode is lithium metal, and the positive electrode is still some kind of transition metal oxide. It could be LFP, it could be NMC or something else. And lithium ions move through the solid electrolyte instead of through the liquid. So when once we get to manufacturing solid state batteries at scale, which is tricky and seems to always be a couple of years off, they're going to need cathode materials, positive electrode materials that are really stable and can kind of sit in it's almost like those peanut butter marshmallow squares, where the cathode particles are marshmallows and they're sitting in a peanut butter matrix, like a solid matrix. You want those to kind of be stable. You don't want them crumbling apart like these polycrystalline materials. So I think it's actually quite likely that these single crystal materials will be used in solid state batteries.
You had to add calories to this discussion, didn't you? You couldn't resist s'mores.
Got me hungry. Maybe I could go for one of those right now.
Well, listen, thank you, Jason, so much for walking us through. I think we could have gone quite a bit longer with questions, but we did pretty well. And Toby, Dr. Bond, thank you so much for coming on and doing this with us. Obviously, some of Jeff Don's magic has rubbed off on you, and you're carrying that torch forward. So we're really thrilled that you took the time to share your knowledge and spend this time with us and answer some questions. So
Thank you so much for the
really
invitation.
appreciate it very, very much.
Yeah, anytime.
All right, I'm going to talk about next month's webinar. And of course, what we're going to be doing is something kind of different. We're going to be welcoming back our favorite EV technician, which is a fellow by the name of David Giles. He's been on a few times. He's a real expert with EVs. And as more electric vehicles approach the end of their factory warranties, David will share key insights on really what to check before your coverage expires, and also how to keep your EV running smoothly once that new car warranty is finished and done. So I think it's a good one. It's timely with all the cars that are coming due. And I hope you'll come back and join us. Mark the date. It's going to be on Tuesday at 7:30 p.m. Eastern Time. So if you've enjoyed this webinar, please take a moment to give it a like if you're watching it on YouTube, and let us know your thoughts in the comments. It's free, and it just takes a few seconds, and it really does help other people find us on YouTube, and we are trying to get the word out about EVs and the technology. That wraps up another edition of Canada Talks Electric Cars. Thanks for joining us. From all of us at EV Society, stay charged, stay curious, and we do look forward to seeing you again next month.